So we're going to pick up where we left off last time. So last time we were talking about nitrogen or actually finished with nitrosoureas and how they alkylate DNA through a diazo species or diazonium type species. It's very reactive, has dinitrogen, the world's best leaving group, and an alkyl group that can react with that nucleophiles, particularly in 7-on-guanidine. And this time we're going to pick up with some other chemotherapeutic drugs. So we're going to start by talking about mitomycin C. So take these mechanisms with a grain of salt. There's definitely too many arrows in one step for this to be happening all at once. So this is more of a cartoon than a mechanism here. But basically what's happening is what we're getting is bioreductive alkylation. And so what this means is that metabolically, somehow, we're getting donation of an electron or two and possibly also a proton. But these electrons, remember, lose electron, oxidize, gain electron, reduced. These electrons are coming from some biological molecule or some biological activity, and they're what's taking the drug and turning it into a chemotherapeutic. It's what's turning the drug into the reactive drug. And so in the case of mitomycin C, what's happening here is that we have reduction here that's going to basically make this we'll start this. They have reduction here of the quinone form to the bisphenol, if you will, or this mixed ether phenol form in this case. And this is attached to an enzyme at that step. And this can then, the nitrogen with this extra added electron density from the reduced form is going to, this extra density that it got from reduction is going to encourage the nitrogen to eliminate the O-methoxy group. And eventually what's going to happen is that you're going to form a reactive species that's going to be electrophilic because you have this quinone. So this is kind of like a quinone methide here. And that species means that you have a lot of pull electronically. You have a delta plus over here where these electrons can resonate to, so a nucleophile can attack over here and we can push those electrons all the way over there. This is, I guess you would call it a vanillogous quinone methide for those of you organic chemistry aficionados following along. That then sets up another, that's right, Michael system, and you form a double crosslink. You form two single bonds to the DNA. It's pretty amazing. It's a pretty amazing setup. So you're eliminating this carbamate type group here. And so you can imagine if you've got two single bonds to DNA, this is on there pretty good. And so that's going to be a strong alkylation to DNA. Another example, here's another example where we've reduced a quinone to a hydroquinone. So here we've done the same thing, where what this means is that it's an enzyme with a reducing cofactor. Remember, NADPH is one of our biological reducing agents. It could also be NADH. And that's donated 2 electrons and 2 protons to the quinone to create the hydroquinone. So this is this is a hydroquinone here, this species here. in this case, this is not all, again, this is cartoony, this is not likely to happen in one step, but you get these exocyclic methylenes here, the methides, and they are going to react with DNA because you can resonate, you can push that all back, and you can get to an aromatic form at the end of the day. There should be a couple of arrows here. Remember, these are cartoony type mechanisms. So an unusual anti-tumor is linomycin. So we'll go through this mechanism, but I will give you a grain of salt, or say take this with a grain of salt, because people try not to use drugs that have these kind of reactive thiols in them because they tend to be smelly. In this case, you got to have an intermediate like this. So you're playing with sulfur oxidation states a lot, which is really interesting, but also can be a little confusing, I think, for people early on. In any case, these reactive species can set yourself up to react so that you have a plus charged sulfur here that can react with the N7 guanine with DNA. But there's another mechanism too that can happen, which is that you can supposedly form OH radicals. I'm not sure if I believe that myself. So one of the ways that I would argue that you're not always forming hydroxyl radicals, and actually superoxide can do a lot of damage. Your book is claiming that you're forming hydroxyl radicals, which are extremely short-lived. But either way, what's happening is the same things happening here in the center. This is all pretty standard way to talk about this, which is that these anthracycline chemotherapeutics, and these include things like doxorubicin, for example, is and adriamycin, that's another one. But doxorubicin certainly is a really common chemotherapeutic for a lot of different drugs. And doxorubicin has set up this quinone structure, right? It has a quinone structure as part of it, what we call the chromophore, right? So this is the colored part of it. And over here, remember, there's a sugar. You can go back to last lecture where we saw that pretty structure of it edge on into DNA with the sugar coming out the front. And what happens is it can gain one electron, and it can go through these one electron pathways where it can turn into a radical anion, and it can subsequently transfer one of its radicals back to oxygen, which in the ground state is a diradical, and that can make superoxide. So if you want to turn superoxide, react superoxide with, for example, peroxide, you can do it a lot of different things with superoxide, and that's why basically the fastest enzyme you have in your body is superoxide dismutase that gets rid of superoxide because it's so damaging. And superoxide dismutase is an example of one of those enzymes that's diffusion limited. So it goes so fast that the only thing that's limiting the rate is how fast a molecule can diffuse into its active site and diffuse out. That's it. And so that's how your body deals with this normally. What this drug does is it's making it next to the DNA. It's making these dangerous radical anions next to the DNA, and these radical anions can catalyze DNA strand breakage. So it's sitting there next to the DNA. There's no superoxide dismutase just hanging around ready to do something about it. And so it's set up to start doing some strand breakage in DNA. And we know that if the DNA strands are broken up into little pieces, the cell's going to undergo apoptosis. It's going to want to die. It can't replicate anymore. The DNA needs to be a linear molecule. And so one of the ways that you can form even more reactive radicals from superoxide is through what's known as the Fenton reaction, where you use iron and oxidized iron, and that can result in DNA strand scission through, say, the generation of hydroxyl radicals, etc. So another way that has been proposed as a mechanism is that this is you're actually complexing iron and oxidizing it to iron 3 through anthracycline type. So again, this is going to be stuff like adriamycin and doxorubicin that do this, where they're creating radicals that break DNA strands. So these guys aren't cross-linkers, they're DNA strand, or alkylators, these are DNA strand breakers. So they're working in a different way than anything we've seen before. Okay, so another chemotherapeutic is bleomycin, and so it has this structure here. This is actually in nature, what this is for, so in the Streptomyces bacteria, this is likely what's known as a siderophore, which is a iron chelating structure here. Sideros is the Greek word for iron, and phore is eater, so it's an iron-eating, iron-binding structure there. And it has a couple of sugars hanging on the side here, and so it can intercalate into DNA, and just like in its, and because it has this disaccharide structure, the cancer cells can think it's food. It has this, which looks like folate, the cancer cells can think it's food. And this is, this is like an amide basically with some non-standard amino acids, and we have a gamma amino acid here, but in any case, what this siderophore does, so this molecule is used by the bacteria to sequester iron, and it actually binds iron very well, and it can do the same thing in the body. When it binds iron 2 that's available in the body, then it can do the same thing where it can generate radicals. And so in this case, it can generate radicals. So they have it over here, the iron actually chelated through some of the histidines. I would argue that you can do this from that siderophore-like structure as well. But of course, you form this multidentate ligand over here as well. So it might just be with the bond links. That works very well through the imidazole type system. The activation, so what bleomycin is going to do again is it's going to generate radicals, and this strand scission, that means they're breaking DNA strands. So I would say here this should be the bleomycin plus iron 2 is probably going to, well, I guess it needs to be iron 3 in the beginning. Anyways, no comment. In this case, they have really? Okay. In this case, they have it going all the way to iron 4, which is a little different than what they have there. I mean, it's pretty hard to isolate some of these intermediates, so some of this is kind of speculative, but the upshot remains that bleomycin certainly does cause double-strand breakage in DNA. So you could propose a mechanism. It's kind of hard to chart a mechanism this fast. The main thing to see here is basically that you can mess with the ribose, the sugar component of DNA, and break that. So the bleomycin can be intercalated in the DNA, and if it's intercalated, let's say So if it's intercalated back through its siderophore group, if this is what's fitting into the DNA, which would likely be the case, right, because it's the right size to fit in a minor groove, then this piece is going to stick out. If this piece is now bound iron, it's going to be active in this way. So there's iron's going to be, this is going to be next to the DNA bases, but this will be sticking out next to the backbone. And if that's the case, that means there's a source of high energy radicals next to the backbone, and that's what can go ahead and break the bond. So remember, this is on the outside, right? This is facing out. So the rest of the bleomycin's over here, the part that has the iron's over here, and this is the part that can do generate a radical to do radical chemistry. There's certainly other drugs available that kill this is an example of a drug that kills hypoxic cells, solid tumors. I can't imagine actually I can't imagine that this drug has got to have some issues. I'm not familiar with this drug, but I would imagine that this drug has not made it. The reason I'm not familiar with this drug is that it is very rich in nitrogen, so much so that you can't take a molecule like this on a plane. You have to put it in a truck. And so I would imagine the reason I haven't heard of it is because it's too explosive to be used widely. But your book talks about it, so there's that. So, I mean, what it does is cool, but it's, at least to my knowledge, is not a widely used drug because it is so obviously runs the risk of explosion. So that's kind of a piece of flair. Okay, so one really popular, I would say it was a really exciting branch of chemotherapy, somewhat recently, was the enedione anti-tumor antibiotics. And so these are warhead antibiotics. And so what you see there is that you see an ene, so it's an alkene, and two ines, Y and E, so it's two triple bonds. And this is going to be the warhead that's going to covalently cross-link to DNA. And so these are actually originally natural products. They were discovered back in the late 70s and early 80s. And there was a lot of work in kind of culminated, I would say, in the late 90s, early 2000s on figuring out how these worked, why they were such good anti-tumor drugs, and how to make them in nice ways synthetically. And so they have these gorgeous structures, like Dynomycin A, for example. There are a lot of these different natural products. And so what this means is that bacteria and fungi, etc., are using these as chemical warfare agents and to protect themselves. And so in this case, right, Dynomycin A is also interesting because it looks like an anthracycline, right? It looks kind of like anthracycline, it looks like a doxorubicin type structure. Here we have a little bit of something that looks like bleomycin. So they all have enes and dienes. What they do is that they intercalate into a minor groove of DNA, and this reaction, actually they intercalate and then they end up getting activated through a radical process, and they affect a radical-based cleavage of the DNA. And so basically something like this happens, and then they get what you would say is a radical source. So they're going to reductively cleave this triple bond into the S minus. And this S minus is going to be a nucleophile. It's going to act as a good nucleophile, and that's what's going to start this whole formation of what is essentially a benzene ring with two radicals on it. So they went from two alkynes and an alkene to a benzene ring with two radicals on it. And so dynomycin again has a reductive mechanism, but it's a different way. So whereas here, right, we have this trisulfide bond that gets reduced. The trisulfide gets reduced to an S minus here, and this S minus is what's going to act as the nucleophile. So it's reductively activated. Here with the dynomycin, we're going to reductively activate the quinone to, again, one of these an activated structure like this. So this is see how it looks like that diphenol structure, right? So that is the activated structure of the quinone. So it looks like two phenols attached together. And so that is what's going to act as your activated species there. Okay, so I'm going to stop there, and then I'm going to do the Bergman rearrangement.